Okay, so what we were doing last time, I thought I had gotten to the point of starting to talk about homotopy types, but I want to take a moment to make a little side digression because it ties in very well. So recall that what we did at the end, or the main thing we were talking about last time, is we looked at the what I call the kind of justification, for lack of a better word, justification for the J, or identity elimination rule, and we showed that the crucial thing was to understand the interaction between the functoriality of the family that you're eliminating into, or functoriality of the target family. I'll just write C because to have you'll remember what we were doing, and between that and between the idea that J sort of behaves roughly like an inductive definition, and I can put it as the elimination form as a recursor. So for the inductive analysis, if you will, for reflexivity of J itself, of how J works itself. So the idea was, remember that the computation rule is if the motive, well, this should really have three arguments, X, Y, Z, C, and the critical thing was we have reflexivity, right? Let's say it's at type some type A, and then we have X dot P or something like this. And the idea was that this had a computation rule that said you can plug M for X in P, and the whole point of the discussion last time was to say, well, isn't it odd that J looks only for reflexivity when, for example, by univalence we have, if we have some equivalence which will consist of some maps, F, G, and something, okay, would be an example of an element of an identity type between some particular A, B, something like that. And we were also talking about funnext. Let me not write that out. We had function extensionality, which was the identity, a path between two functions in the function space, and I mentioned there's going to be other things. So the idea was to say, well, a naive reading of what is going on with identity elimination, it looks inconsistent because it seems like you're only checking for reflexivity, but then you're throwing in some random other things and somehow it works. And the somehow it works was traced back to the global, if you will, functoriality conditions. I wrote functionality because I'm used to that from my background. No, it says functoriality, yes. The functoriality of families, that is the global idea that everything in the type theory respects path structure, and we exploited that in order to give a justification for J. So I thought about it over the weekend when I was thinking that actually this would, before I go on and talk about homotopy types, it might be worthwhile to look at a very concrete example in more detail, which foreshadows some things we're going to do a little bit later. But what I'll do is I will do an ad hoc treatment of a particular type that will be an instance of a general schema later on, which I've talked about a little bit before, which is the interval type. Okay. And we usually write this as I. And it's a good example because it's a counterpoint against, it makes a concrete example that I could put here in the ... of another thing that introduces a path that doesn't seem, it literally, quite literally isn't reflexivity, but nevertheless the whole theory holds together in a way. So what I wanted to do is I wanted to broach this because it also allowed me the opportunity to say something about homotopies and paths and function spaces that have been hanging around for several lectures, and so I can kind of tie that up and then also amplify the points I was making last time about the identity elimination. So what is the interval type? So we can say we're going to have, in any context here, we're going to have a type I, which will be the I formation rule. Okay, I'll just put the key rules down here that matter. And you recall that the picture that I have in mind is something that looks like the unit interval. I'm going to have two endpoints, and if I need to be really finicky, I don't want those to be natural numbers. They're just names that I chose for the endpoints. And so the names for the endpoints are 0 and 1, and then there's something that connects them, which is a segment. So we're supposed to think of this as something analogous to the unit interval that comes up all the time, particularly when, in a moment when I mention we define homotopies. The analytic treatment of what is a homotopy relies on having the piece of the real line around, because it's typically done in that setting. You're working in topological spaces and you're taking advantage of a piece of the real line. But here we're going to do an abstract account of it. And so the idea is, if I didn't really give you it before in full detail, because it's going to bring up some topics that we're going to have to think about a little bit more later anyway, so this was a good opportunity to bring those up. So let's look at the introduction rules. Okay, so I'll put 0 like that. So we can say that 0, or maybe 0i to be really finicky, is an element of the interval. So we have these so-called 0 cells, or this is the introduction 1 that we put in here. So these are sort of the 0 cells, or the objects, or the elements, whatever you'd like to say, of the type I. So that part is like normal. Okay, it's perfectly like usual looking thing. In fact, so far, if I were to stop here, you would think, well, all I'm really defining are the Booleans, which is actually true, insofar as I don't write the next line. But then the idea is that in order to represent this idea of the segment, which we often think of somewhat sort of geometrically, I guess you could say, the path, that there exists some way to traverse from 0 to 1. You can walk along that path. Remember, in the idea here with homotopy type theory is we think of those paths, the existence of those paths, as being equations, because the paths are reversible and they are composable, so we at least get an equivalence relation, and then everything in sight respects it. The idea of functoriality, the app that we talked about before, the apply to path principle, then that allows us to say that, well, it's a perfectly good notion of equality. It's an equivalence relation that everything respects, so we can just say that is our notion of equality. If you like, you could kind of think of it as modding out by that with respect to some underlying idea of equality, but anyway, there doesn't seem to be any point to doing that. We can just take that as our notion of equality. So what's going to happen here, and it seems a little bizarre when you think of it from the point of view of equality, is we're going to also postulate another introduction rule, which introduces the segment. Where else is that going to come from? And what does it mean to introduce the segment? Well, the only thing it could mean under the current setup is that I'm just putting in a particular path. So this formulates between 0 and 1. So I have another introduction. So I have 3 introduction rules that are going on here. In some sense, these are the 0 cells and these are the 1 cells. That is, I'm introducing these as ordinary elements, and here I'm introducing them as paths. Okay, so that's the idea. And so this is the thing that, when you think of the identity type as being some inductively defined type, as we talked about last time, this seems like blatantly wrong. You can't just go around and decide to chuck in new elements of some previously given type just because it suits your convenience at some moment. But oddly, with the identity type, has a special role in the theory, and because of that, a special role in the sense that everything knows about it and knows how to respect it, then it's actually legitimate, even in the face of having a recursive elimination rule like that, to throw this in. So that was the subject of our discussion last time and lecture last time. But here's one where, I'm really flat out chucking something in here to the identity type. So it's an instance of the identity type that we haven't seen before, so that's part of the issue, is because the identity is a family of types, or a relation, and so this is a particular instance of that relation, and it's not like I said, the reason to write 0i and 1i is to make clear that I'm not actually saying this is an equation between the natural numbers 0 and 1 or something like that. So I wrote it like this, or you could come up with some other crazy notation, whatever you feel like, for the endpoints. But I want to make clear that this is an instance of the identity type that has not previously been considered or populated before, because the introduction rule, which I didn't write down, would only have said 0 is equal to 0 and 1 is equal to 1. And now this is a new thing. And that's sort of part of the secret, because I'm not disrupting a previously given or previous conception of this particular instance of the identity type. All I'm doing is enriching the concept of identity, or the relation of identity, in a particular way. So that's part of like why this is actually a sensible thing to do, even though on a naive reading it's not. Okay, so those would be the introduction rules. So the question then is, what should be the elimination rule for such a thing? And as usual, what we do is we state these in a dependent form. So what we're going to do is we're going to think in terms of a mapping out property. So we're going to think of this as being these introduction principles that I've given here. I'm going to think of those as being I want to invert those. I want to think of this as an inductive definition of the type. In other words, that that in some sense I should be freely generated by the existence of these 0 cells, 0 and 1, and the existence of this path. So that the way you express the free generation is by some kind of an initiality requirement. So that what's going to happen is there's going to be a map out of I, okay, which there are different ways I can present this, and one would be this. This is a little bit of a, or I can do it another way, which is, let's write it like this. Treat it as a map rather than as a function. We can do it like this. And the idea is we're going to map out, okay, of I, and we're going to wind up somewhere. And where we're going to wind up is C of x. All right, so we're going to end up proving that if you think of it propositionally, some property holds of x, or you can think of it as a family, or we're going to compute an instance of the family C of x, and we know for general reasons that that's the same thing, but sometimes it feels nicer to read it propositionally. Okay, so you say you have a mapping out property and you want to get a C of x. So how could you possibly do that? Well, if you just think of this as freely generated by the introduction rule, so we're applying Genson's inversion principle here, then we're going to have a recursor, and then making up ad hoc words for all of these becomes pretty much impossible. So we'll write that rec sub I because it's unimaginative. I don't know what else to call it. Okay, and what it's going to do is you can think of this as working on x, okay, working like that, and it's going to compute C of x on that data. And then I'll give some definitional equations here that say something about how they compute. So clearly, if you follow your nose in the usual way, and this particular move we do next is something that isn't found in Genson. It's always kind of remarkable to think how many things in computer science anyway and logic are basically either explicitly or implicitly in Genson's work. But this is not one of them. But we'll get as far as I know anyway. So we'll do it like this. But if we follow along this principle, then clearly x you think to yourself, well, x could either be 0 or 1, and so I've got to cover those two cases. So I have to have, let's say, an m naught, which is C of 0. Oh, what is C? C is something that is a type which we say is an inhabitant of a particular universe. We've talked about that before. So we have m0 is so to say, if you think of this as an induction principle or a case analysis, I have to cover the case of 0 and I have to cover the case of 1. Clearly, because I have 0 and 1 are in there. So the arguments to this guy will include m0 and m1. And then the other thing is, how do you account for this? How do you account for this behavior, right? We have to say something about the existence of the segment. Well, there are different ways of thinking about this, okay? One way, and I think the thing that's most profitable here, like in terms of like just your psychology of understanding of what's happening, is to remember that a lot of times we will write this as 0i equals I, 1i, that's what that is saying. And admittedly, it looks a little weird to introduce two things only to immediately tell you that they're equal, because you ask yourself, then why the hell am I introducing two things to begin with? But let's not worry about that at the moment. Okay, it feels better if you think of this as a data structure, and you're just saying, well, there's this, these are the endpoints, and there's that piece of data, and never mind. On the other hand, when working in the elim, what I find most natural is to think of this as an equation, nevertheless, okay, despite the fact that it seems weird to introduce such an equation. And then what you want to say is that the reasoning here is well defined, because I need to guarantee that everything is functorial. I need for the recursor to respect the equality on I. Okay, that's the intuition that I'm trying to convey here. And when you think of this propositionally, it throws very much into your eye that I have a requirement that says, well, whatever this guy does on 0, which is going to be this guy. So in fact, I could do this right now. Oh, and by the way, using my typical notational conventions, this should be parameterized by the motive. I forgot to write that down, but anyway, so we have the motive x dot c, and even given where I've gotten so far, I haven't finished, right? You would say, well, this is going to be obviously m0, which will be c of 0, and then we'll have a similar thing, x dot c and 1i and m0 and m1, and well, we're going to fill some stuff in, but at the minimum it's going to be that, because this is like a Gensen-like intuition about what we're doing. So given what we've written so far, it's sort of clear that's what we're supposed to be doing. And then the issue is, what do we do about this and other introduction rule? Well, the other introduction rule amounts to saying that there's an equation in the interval between 0 and 1. And so if this is going to be functorial in x, then the only way to do that is to say whatever this guy does on 0 had better be equal to whatever it does on 1. And so by this principle that I've written here, that means that m0 has to be equal to m1. And of course, that's proposition, that seemingly a proposition when I say m0 equals m1 is really a type. So there's really a proof, p let's call it, that says, and now again I find myself psychologically wanting to use this notation. Okay, but of course I could just as well have written that id I m0 m1, but somehow it feels better to do this. And then you put that data also in the recursor, and then there's going to be a question which comes here, which I'll get to in a moment.
But m0 and m1.
Oh, and then this should be a p. Did I make a mistake?
m0 and m1 are.
Oh, and c. Oh no, I have to do one moment. Let me check my rule. I've got to worry about that. It's a path over the segment. Yeah. So what we do here is this is a path over the segment. Right. Sorry about that. So remember, we talked previously about path over. So in this particular case, when I have x dot c, so I have a family of types, and the endpoints, remember the picture we had is this. With path over is we have two fibers, right? In this case, it's the fiber over 0 and the fiber over 1. But in general, we talked about it. And we have an element over here, and we have an element over here. We said the idea of path over, which I'm writing here, is that these guys are connected by a segment. And so what we're saying that these are pseudo-equal, I don't know, are correlated by the segment. There are different ways of saying it. That these should somehow, I don't know what to write here, but these should somehow be related. And what that means is actually that this can be transported here, and then within that fiber, those are equal. Or equivalently, this could be transported over here, and within that fiber, they're equal. So we talked about that notion before. So this means equivalently, there's two different ways of doing it, but one would be you transport in the family. This is sort of sigma c. This is the total space of x dot c, and then what I translate in that family by the segment of m0, and I equate that in I. It's really, this is x colon I, so somehow the notation you should be able to recover everything on the right from what I have on the left. So this is the m and I and m, or equivalently you could do it the other way around. And in fact, one of the motivations for introducing transport, path over, was to avoid this thing. So I can, if the segment a priori, although it's a reversible thing, it's in fact oriented in the first instance, and then it's seg inverse that goes backward, you'll recall. And often we just don't notate it that way, but that would be the thing to do. And so this is the transport by seg. Well, that's often written seg lower star. Okay, and this is seg inverse lower star, which is seg lower star inverse, so you could just ambiguously write it like that. And and so you can do it either way, like that. So going back, so this says that whatever you do on 0 and whatever you do on 1 have to be the same in the sense of the same that I'm talking about, meaning they're correlated by the segment in the family C. So that's the way I think about that. So it's a well-definedness criterion. You could, as I say, you could just replace that by this, okay, to get the transport properly. So in particular, by the way, if the dependency is degenerate, okay, then we observed previously that by these definitions, if I have a constant family, I write it _.c, and we have some path p, which doesn't matter in the indexing, the vacuous indexing, that just is, okay, that's going to be equivalent to being equal in whatever you're indexing over. So if you're indexing over A, then this is just an equation. So the idea would be if there were no actual dependency, then you really would be saying that M0 has to be equal to M1.
I think like on the top, those types have to be C of M1 and C.
Oh yeah, they should C of M. This is C of, yeah, I do that kind of thing all the time. C of 1, and this would be C of 0. I mean, that's the whole point, right? Yeah. I don't know why I wrote I just was.
And I'm not sure exactly how the types work out on the bottom.
What?
On the thing you just wrote, I don't think it should be A.
It's going to be the constant C. Yeah. Yeah. Sorry about that. Okay, so that's because that's what I was referring to. It's a constant C, because when this is constant, okay, then nothing will depend, and then you really are saying they're equal. So constant means there's no actual dependency, so the total space, one could say, has like one fiber. You could think of it like that. And then you're just saying they're equal. Okay, so that part is good so far, and I put the p's in here, okay? So I've written like that. So you have to have some data. So in the typical proof relevant setting, we have some data, okay, that says that witnesses the well-definedness of the thing. But what does that well-definedness amount to? And now here comes an issue that is I think, in my mind anyway, as yet unresolved, because it's to do with the computational interpretation of everything. But the idea is that what this is doing is guaranteeing that it's telling you the way in which, if you would like to say that, or it's witnessing the fact that rec blank da 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 is functorial as it must be in the free variable x. Okay, so what that means is the following kind of thing. I have to notate this. If I do an apply to path, okay, and then I'll write it like this: lambda x rec let me skip well, I'll leave the modal. I'll put it all in just once, okay. It gets a little heavy, I admit, but okay. So in other words, thought of as a function of x, the thing that you're recurring over, what does rec do? And in fact, this should be probably, well, you can write it like this. There should probably be a DApp. But I think I wrote this as a DApp or something before. But in other words, when I do the apply to paths on this thing, okay, and I apply it to seg, all right, that's the path that I'm actually wanting to consider. And now the computational issue. The thing that is kind of natural to think is that this would be, and now of the appropriate type. And we'll write it M0 correlated by seg in x.c, that comes from here, okay, M1. And this is, as yet in my mind anyway, unclear whether that should be a definitional equality or not. Okay, so that's where the issue comes up. So this we get as definitional equalities because this is, so to say, a la Gensen. So we're kind of following our nose here, and when we work with the zero cells and look at the behavior on the zero cells, we feel like these ought to be definitional equivalences because they always were, and that's the story. But now we have a slightly different thing going on, because we have to consider in what sense is this thing functorial. So this is a map. So the idea is that this should be functorial, as I mentioned a moment ago. This should be functorial in X, right? In X. In other words, it has a property that when given an equality between two elements being plugged in for x, in particular an equality between the distinguished elements 0 and 1, then I expect that equality to be carried over into an element of C0 and C1, and you would think that this ought to be a definitional equivalent, so this should be P. Okay? We could, and I think if it might be done this way in the book, I don't recall, this might be stated in the book as an equality rather than a definitional equality. Okay? It's not going, it doesn't, in a certain sense, from a certain point of view, it doesn't hurt to do this. This would be a stronger condition. This would be a weaker condition, because if this holds, then this holds. But if you're going to have a computational meaning to everything, well, making these things weak is going to complicate matters anyway. So I just thought, for right now, I want to broach the subject and not like make a definitive statement about it, because I'm not sure that anyone knows, or certainly I don't know, what the really right thing to do here is. But if I follow like the Gensen thing, but extending it to the next dimension, then you could expect that I'm going to stipulate that this is the way DApp has to work. Okay? That DApp, when applied to the segment, ought to pick out the distinguished path P that you gave as part of the data of the recursor. That would be the principle of it. Okay? Of course, if you had some Q which was equal to P, then of course it would be true. First, by definitionally, it would be P, and then P is equal to Q. So in a weak sense, it would be Q. So you would get all the things you would kind of want, but it feels as though this ought to be the case. Okay, so that's what I would say. But notice, in a certain way, it means that I'm patching the meaning of DApp, because DApp was this function, right, that we were thinking here. So in this case, you know, DApp is, you could think of it as taking, more generally, pi x in a, b, right? And what it does is, if you give it, I have to give it a name. If you give me a path in A, let's call it between x and y, then what it gives you back, let me erase here to give myself room, what it gives you back is a path, a correlated path, and we could write it in, well, now the notation gets a little messy, but xb correlated by p, I don't know, to fx. This should be given a name too, so let's call that f, okay, and then it would be fx and fy, right? Okay, that would be what the generic type of DApp. So if you think of that function as having been given once and for all already, then whatever its definitional properties are whatever its definitional properties are, and I don't have any business throwing this in after the fact. So, you know, what can I tell you? I don't know what to tell you. Maybe we shouldn't think of this as being a function, really. Maybe we should think of this as a primitive, that is, whose definition is being specified as we go along. I don't know. This is where the wooliness comes in about the computational meaning. If you're not worried about the computational meaning, then you just make these equations, and then, like, that's the end of the story. Okay? So that's the way I currently think about things. Okay, so that would be a definition of what the recursor is and how you would do that. And so now I wanted to relate paths to homotopies, which is what I said I was going to do before. And so this is a good. So my first point is, bringing this up now foreshadows things to come later, but moreover it ties in very well with our discussion of the identity elimination and the interaction between the various components of the theory. Okay, so that's like first thing to think of. So now the other thing I wanted to mention, which is kind of fun, is the following fact. So we can look at this thing. If you look at what is called the total path space of a type, okay, I'm going to write down an equivalence, but this guy could be written by various things. In my notes I wrote it integral id A, or you could write it the paths over A, or something like this, or maybe you should write it plural or something, I don't know, something like that. So you need a notation that sort of says sum up all the paths in A. You know, pick your endpoints and then sum up all of the paths between those endpoints for all possible endpoints in a particular type A, X and Y and A. That the total path space turns out to be equivalent to the maps from I into A, which is kind of cool, right? It's really nice because based on, the analytic approach, right? So this analytically, this could also be thought of as the path into A. So I'm not going to give this a name different from that one because I'm about to prove that they're equivalent. But the idea is that you might call this, I don't know, don't mind me, you might call this the conventional path space. I don't know, it's a little problematic because conventionally, this would be a piece of the real line, and this would be maybe a topological space, and then you're saying a path in A consists of a set of points, okay, maybe like that you could say, one for each thing in the unit interval, where this is what 0 does and this is what 1 does. This is the image of 0 and this is the image of 1, and you find that line in there. So what I'm going to say is, and it shouldn't be surprising once you get your head around it, because remember, what is the content of saying something is I arrow A, right? This is a three-part thing, because it's a mapping out property, right? There's a mapping out property that says you're mapping out of I into A, right? So if you think of Genson's unicity principles transposed in the exact way I'm mentioning over here, that the inversion principle is being transposed to the higher self, then you would say, look, this guy must be given by three pieces of data. It tells me what to do, which would be A naught, let's call that A naught, right, the endpoint here. This would be A1. It must be given this way because the uniqueness property of the mapping out would tell us that. And it must be that it turns the segment into, well, the path in question. Okay, let's call that guy P, which is a path between A0 and A1. Okay, that's the intuition, right? The idea is that, right? So we say this data must be given like that. And in which case you can see what the correspondence between these two things must be, right? Because now if I go, let's say, from top to bottom, so we'll go like this, if you don't mind me using pattern matching. If you give me lambda x, y, and z, or let's call it p, or remind you that that's a path. So this triple is in here, okay? Then I want to turn that into a mapping from here. So how do I do that? Well, a mapping from here is something that takes a z, or let's call it an I, or a lot of times people write t because they think of this as sort of time, okay? So however you wish to like it, however you wish to write it, I'm going to take in t, and now I want to send this according to this data, right? So what do? I say, well, I'm going to do a rec, okay? The motive is going to be constant, okay, because in this case I'm doing a path into a fixed target type A. There's no dependency. The family is there. So I have a constant motive that's written like this. And I recur on T. So T is, so to say, ranging over the unit interval. So T is somewhere along, conventionally you can kind of think of it like that, as sitting along somewhere between 0 and 1. That's our time. And we say, well, at time 0, you should tell me the answer is x. At time 1, you should be at y. Because these were the inputs, x and y are given here. So here's my x, here's my y. And the path in question that you should take from x to y should actually be p. Okay, so that would be the definition. So this thing itself, okay, call that H for homotopy, is an H with this behavior. Well, this notation is a little bit cheating, right? Because what I'm really saying is H, when applied in the sense of a zero cell, that has to be, let's use this notation here, A0, and I'm saying H when applied in the sense of a zero cell, this should be 1. And then I'm saying if you app H, or we usually write that as a subscript, to the segment, well, that's your P, okay? That's the P in question that you're trying to pick out. So this recursor is defining that H. That's what I'm hoping to do, right? And now we go the other way around, okay? And what should the other way around be? Well, I'm going to take in such an H, right? And now I want to spit out a triple, so it's pretty obvious what I should do now. What should I do? I should say, well, your starting point is H on 0, your ending point is H on 1, And what is your path? The path between them is app-h to seg. Oops, I'm using angle brackets. And that should be app-h to seg. Okay? Because it says h, you see, being a function, has a functoriality property. Namely, it knows how to respect paths in I. And, you know, the unicity principle makes it blatant because it says that h must actually be given by a recursor. But even without that, all I know is that I do absolutely know that h respects paths, so I get to exploit the fact that h respects paths by calling apply to path with h on seg, and that will be my path. And then you can check then, just I'll leave that as a homework thing, you can check that the required alpha and betas exist to show that, let's say, this is quasi-inverse, this with these data is quasi-inverse of that, and then that establishes the equivalence that I wanted to mention. Okay? So when I first saw this a couple of years ago, I thought that was like, it really clicks into place audibly, and you feel, oh yeah, that's like really great. Okay, so that's like really makes perfect sense that our conventional understanding of paths lines up with this abstract type understanding of paths, where we have an abstract type id or path, which characterizes the paths in a space, and lo, it really works out perfectly, right? That's just like exactly the thing you would expect. So, and then that has an amusing consequence, which I will then explain because it's related to other side remarks I've made in previous lectures. So I want to clean those side remarks up. Which are the? Yep. Sorry. Mm-hmm.
I have a slogan that captures what you were.
Okay. Sure. Go.
So the slogan is: in classical homotopy theory, we have the interval, and we use it to define the notion of path.
Oh, right.
Out of the interval. In homotopy type theory, we have a primitive notion of path given to the identity type, and we use it to define the interval.
Perfect.
Free thing.
Yep. So that's perfect. Because notice, right, the primitive notion of the requirement of functoriality, to even say what it is in this setting, you must already know about the identity type, which is the primitive notion of path. So you start with the notion of path in homotopy type theory, and then you define what the interval must be in terms of that notion of path. I'm just repeating what Steve said in order to possibly amplify it. And then from lo and behold, then you get from that the convention, for lack of a better way to describe it, the conventional notion of path. I don't know what else to say, what other words to use for that. Okay, so we do that.
When you want to check those alpha and betas,
Yeah.
do you need that equivalence you give to be definitional? The third one?
When I roughed it out, it looked like I was using the fact that it's definitional, but I'm not positive if you need it. So you're going to have to check that. Okay. So that's a good question. Okay, so now the next thing I wanted to observe, which is kind of an amusing thing, which is it's kind of fun, which is the following thing. If you look at, or let's do it in stages. If you look at the total path space. So I want to look at the total path space of A arrow B. So we just said that that's equivalent to A arrow B. Okay, so we write it like that's what we just said already. Okay, so we just finished proving that. Now, by things which I've said to you before, we can now uncurry this guy and make that equivalence. So you can check that that's a valid equivalence. So we uncurry it. So we have I or A or B. Well, we'll just take them both at once. Okay, and for reasons I've said to you before, I can also equivalently, it's a standard thing like in categories, there's, you could think of you could reverse the order of the product and you get an isomorphic thing. So this is A cross I arrow B, right, like that. And now I can curry that and I get it to be A arrow I arrow B again. Which is, a significant thing. In fact, the only reason I brought this up is because it has some bearing on something I'm going to say in a minute. But really, this is the relevant point. So this is by various standard manipulations of a very familiar kind. What I'm saying is a path between functions. So we have some endpoints f and g. We don't know what they are. Let's call them f and g. And I have some path between them. Well, that's really a homotopy, right? Because it's telling us that generically in x, there's a path between fx and gx. Okay, that's what's going on. Why? Because for every x you take in here, you're going to get a path, a conventional path, from I to A arrow B. So this is really, by applying the remark again, this is a path in B. Okay, so we could write it like that. So what happens is a path in a function space is a parameterized family of paths, okay, in the range. So it's kind of cute how that works out. And in fact, if you trace that out in more detail, you can get out that function extensionality, which we've talked about before. Function extensionality, remember, says that if you look at A arrow B, F, G, that is the space of paths between particular endpoints F and G. The Funnext axiom said there's an equivalence between that and the homotopies. And the reason now you can see the reason why I called those homotopies, well, depending on your personal preference, but if you had a prior notion of homotopy in terms of mapping out of the interval, it now makes sense for me to call that a homotopy. That's the point I wanted to make. Otherwise, if you didn't have that prior notion, you just thought, well, that's the definition. Okay, that's true. So it could just, that's the definition of a homotopy. So the idea is that a homotopy between F and G is a path between F and G. There's an equivalence between them. So the cute thing is, so if you'll recall, going in this way, that's just a definable thing. Okay, you just do a path elim. It's basically apply to path. Apply to. You could just define this. We did this before. Okay, so we did this earlier, and then we said backward. We took this as an axiom. Okay, up to this point, and I've made my complaints about axioms previously, but in the current state of affairs, then we have axioms, and axioms are like Funnext. Okay, so we took that as an axiom. So the interesting thing here now is that in the presence of the interval, you can actually define this guy. So we can define a map that says for any x id a fx gx here, and then show that it's a quasi-inverse of the one that goes from left to right. I won't give all that detail here, but the gist of it is, what happened to us before is we said, I didn't actually give a proof, but we said that there is no, apart from additional assumptions like the interval or all these things, but when we worked in ITT, we said there is no map that goes from here to here, and in fact that's been proved. You can exhibit a model in which that is to show that there isn't. So there is no map from here to here in ITT, so we just threw one in. But now that we have the interval, we actually can define this map. Okay, this is what we do. So how do we do this? So suppose it's going to look familiar because it's exploiting the argument I gave before. Okay, so you suppose
B instead of A on the end.
I better follow my notes. Okay, so what did I make him?
On the end, it should be
for it.
B, yeah. So you don't come to class usually, but basically I make one of those mistakes every 5 minutes. All right, so that's like, I honestly, right? You guys will agree. Okay, so, so sorry, thanks, yep. Okay, so that's B. I thought you said P, and I was wondering why you were bringing up P. Okay, yeah. Anyway, yes, B, sorry about that. So you suppose you're given that, okay? So what we want to do, right, the way to think about it, I like to write it as, I'm going to exhibit something or other, okay, which is in A arrow B. This is sort of the proof relevant way of saying to show, right? I find something which is in there, and that's the thing I'm going to do right now. I'm not going to prove that it's an equivalence. I just want to do that. So what we do is I define. So I want to get a path from F to G. So a convenient way to get a path from F to G is to define something, and the way I do it is by exploiting the thing I was doing before, and I'm going to define a homotopy in the conventional sense as a mapping from I into A or B. It's just a nice way to do it, okay? And we're going to define it by these equations. So the way I did it in my notes, let me just write this down so I don't get myself too terribly confused. So we define it by H twiddle is defined to be, H twiddle is defined to be, what we do is we take lambda I or lambda t, whatever we call it, think of that as the time thing, and we take in x, which is going to be here, and then I do something parameterized by x, which I wrote with a double twiddle of t. Okay, so it's written by that. Where, okay, what do we do is we say, fixing x as a parameter, so h double twiddle, what does it do? Well, I'll write it in a pattern matching sort of style, and you have to see that this can be turned into a recursor. That's the thing that has to be done. Okay, so I'll say, well, what this guy does is at time 0, it's going to be fx. None of this is going to be surprising to you now that I've set everything up. Okay, at the other end, it's going to be gx. And on the segment, and here I'm using that definitional kind of possibly questionable thing here. It's going to be the given h that we are given here, which is a path abstractly like that. So now, if you look at it, right, then what is it that goes here? The thing that goes here is you do an apply to path of h twiddle to seg. So what is h twiddle? It's I arrow A arrow B. So that's the kind of thing that can be applied to a path because it's a function out of I, and a particular path. In fact, the only one we can concretely get our hands on in I is seg, okay, and we write down seg. And so the action of that will be, if I give you an equation in I, it will turn it into an equation in F and G. In other words, it will give me that path. And so this is the guy. Okay? And so that's how it works. Okay? So we get that. And so that, and then you can show that going back to the previously definable thing and doing a little work, you can end up showing that is the other half of an equivalence, or quasi-inverse. Giovanni, did I screw it up?
So Bob, are you assuming that the path over for a constant type family is really the same as the non-dependent path? So I think that's a
Well, there's certainly I can get this much. And do you think I need more than that?
no, but maybe you need to write some conversion function there down the bottom.
Write down the what?
H of x is a non-dependent path, and the set is requesting a dependent path over it.
Yeah, so you're saying this will come out to be a path over something, but this is a constant family. Is that what you're asking?
There's an implicit conversion in order to make.
Yeah, so in other words, if I only, so what Favoni is saying is this. If this is known only to be an equivalence, then there's coercions back and forth between them. So officially what's going to happen is when I do an app twiddle h to seg, if I look at what's going to happen here, I'm going to get a path over relationship. And then you need to apply this equivalence. Is this what you're saying? Did I get it correctly? To get yourself a plane path. Yes. So actually, I'm probably off by a coercion here. Okay. In my formulation. Did I answer your question?
Right.
Okay. Now you're pointing somewhere else. What?
And also the code there.
Over here?
Right. The P.
Here, you mean?
Okay,
I'll have to, so the note takers will check me on this, okay? I might be off by a coercion because this is not literally that, but is equivalent to it. I don't recall actually, but yes, because this is defined in terms of a transport, and unless I knew this was reflexivity, I wouldn't have any particular definitional equivalence here, I don't think. So yeah, probably I'm off by a coercion. Okay, that goes back and forth between these two. Yep. So actually, that's a nice point. Yeah. As long as yes, you're quite right. And even if I didn't state this using path over, I would still have a transport in here, and then I would still have to worry about calculating that transport weekly in order to, because there's a pre and post composition involved with working out what the coercion means. So I would have to do a pre-composition. So you're right, I'm off by a coercion. So note takers will figure that out. Sorry about that. But this is clearly the idea, right? Okay, so what's going on? Anyway, I found that thing particularly cute, and it's a nice counterpoint. I'm finding where I am in my notes now, working back and forth. Oh yeah, I have some nice things I want to talk about. Okay, so I have, it's a nice counterpoint to the discussion that I had last time about the behavior of J and the identity elimination. Okay, so that's why I did that. Okay, so that cleaned up a bunch of loose ends that we've had so far about about homotopies and the relationship between the paths and the mappings like this, and that's that's one of the more charming things I think about homotopy type theory, is it all just sort of clicks audibly into place, like right at this point you just think, oh yeah, makes perfect sense. Okay, so we're good with that. Okay, so all right, so that's enough. Okay, then I want to resume the discussion that I broached at the very end last time, which was where we were talking about homotopy types. Okay, so this is where we got to. Okay, so we're okay. I'm going to start erasing. All right. Okay, so give me a few minutes to erase. All righty.
While you're erasing, I'll ask you a question.
Okay.
Has anything like an interval type been considered previously in type theory for any purpose? Or is it a completely new kind of type constructor?
It's new to me. It was new to me when I first learned it a couple years ago.
I've never seen anything like it.
Yeah, no, I don't think so.
Seems to be a new thing.
I don't think so. So that's kind of cool thing. But I was trying to, well, it's erased now, but I was trying to say the full development of Genson's ideas may well address these questions about how or whether that should be definitional. And I tried to bring out all the things that are problematic about it, but it feels like one should eventually have that. Okay, so now what we talked about last time, what we set up, and I want to go through it with you, is, okay, we defined the following idea. We said that type A is a set, which is also called a zero type for reasons that will come up later, or it's also called an H set. Sometimes H set is a little better to emphasize that we mean if it's meaning that it's homotopically discrete. Okay, if and only if we take any x and y in A, and we take any two reasons why they're equal, those reasons are themselves equal. That's the sort of setup. So this type here could be taken as the definition of is set of A. Okay? And so far, this is all we did. Like, we just defined the notion of what is a set. We haven't defined anything else. A little bit later, I'm going to say something about, you could you could explain it this way about the notation is a set, okay? I'm going to sort of justify using that notation. But for right now, what we want to say is any two paths between any two elements are equal. So things can be equal in at most one way. That's another way of saying it, right? So it's homotopically discrete. So what we said here is it's homotopically discrete, meaning that up to higher homotopy, if there's an equation, if you have two, so to say, if you have two equations between them, those things are in fact equal. Maybe these elements are all by themselves, okay? Who knows, okay? And everybody has sort of reflexivities, and that's what what I mean is that the identity type, the path, the identities, I knew I didn't write something correctly. So if you go one level up and look at this as the identity of A between X and Y, so we have a P around here and we have a Q around here. They can't be equal. They can't be equal. There can't be a path between them. Well, yeah. Well, anyway, what am I going to say? They're all equal to their paths are equal to reflexivity. If there's a path between them, you can go here, you can go here, and that loop is equal to reflexivity. Okay, that's a way of saying what's going on. Okay, so there's at most one way. Okay. There's at most one way to say the two elements are equal. So the thing that I was observing last time and I want to observe now is a property of ITT. So I basically want to say approximately that pure ITT, this is a way of saying it, pure ITT is a theory of sets. This is like, I'll put it in quotes, okay? And the way I'm going to do this is I'm just going to go through all the constructions of ITT, and I'm going to say every one of those is a set in a certain sense, which I'll explain. So we'll start out. You'll see what I mean in a minute. So, and that all of the constructs of, or a better way to say it is, all of the constructs of ITT preserve the property of being a set. So, for example, I can say 1 is a set. Let me just write 1 as a set to mean is set of 1. Okay, like this. Okay, so we'll say that 1 is a set. Well, why? Because we proved, or you did, that id1 xy for any x and y is equivalent to 1. So there's at most one proof between x and y. So that forms a set. Okay, so that's good. So we're starting. And then this is all going to extend is the idea. So the idea now I can write it like this. If A is a set and B is a set, then A cross B is a set. Okay, so I'm going to claim that this is a derivable rule. Okay, so that's the idea. Okay, so what happens is we know from previous discussion, if you look at the identity type between x and y in A cross B, we had a previous discussion that said this consists of a path between pairs is a pair of paths, okay? So we proved this previously. So you can, oh, sorry, that should say second. Okay, so second to x and second to y, so we do this. So the idea is if you have a path in and between x and y, then what do we know? Well, then as we previously discussed, this can be thought of as this apt2 business between the pairing function. It's basically an eta expansion of paths, if you will, between apt first of p and apt second of p, am I right? Yes, apt second of p, written like that. And then similarly, if q were in here, a cross b, x, y, then the same thing, oh, this would be, sorry, equal to p, all right? So p is written like that. And similarly, apt2 of pair. So you can see where this is heading now, right? Apt first of q, apt second of q is equal to q. But now you see, this is like the typical strategy like we do in type theory. This is of a smaller type, right? The type of this is that's going to be a path in A. In other words, this is going to be id A, because I'm using this projection here. So this is id A. Well, let me not write it out. And then here, this is in id B, which we're assuming are sets, okay? So we know, because A and B are sets, then what do we know? That, well, component-wise, app first of P is actually app first of Q, because there are only one path between any two things. And similarly, app second of P is equal to app second of Q, and therefore, right, P is equal to Q as an element of id A x y, and that's what it means to be a set. Okay? So that's what we're doing. Okay? So now we have the product. And then you can do, I'll just leave it out, okay, 3, or let me not call it 3. Similarly, you can do, it's a little more complicated because there's some path overs involved. You can say if A is a set, and for x in A, B is a set, then you can show me that sigma x in A, B is a set, more or less by the same argument, but with some care having to do with families and dependency. Okay, so we can do that. So that's the, you see what, now you can see what I'm doing. So what I'm doing is, and in fact, if you look at the NPS book that I put on the web page, the 20-year-old book about ITT, they actually use the terminology set. Okay, I don't think they were thinking of homotopy sets in this sense, but they called them sets. So conveniently enough, okay, they called them sets. And so what I'm doing is I'm saying, well, insofar as we interpret set to mean that we have at most one proof of equality between any two elements, then indeed ITT is a set theory. So that's sort of nice. The terminology, you could look at this as saying the terminologies are coherent in a reasonable way. So you can prove that 0 is a set. Well, that's trivial because there are no elements of 0. So you can prove that the identity, the path between any x and y and 0, which don't exist, is non-existent. So that's no problem. Okay, so you can see where I'm going, and I'm going to then say if A and B are sets, then A plus B is a set. And we can do it like that. So how is this going to go? Okay. Well, okay, let's watch, because we did a lot of work. I spent a whole lecture on this, more or less. And so what we did is we said, suppose we have x, y, and A plus B. That's what we're doing. And we have PQ, our paths, in A plus B between x and y. Okay. So now what we want to do, just to remind ourselves, we want to show that P is equal to Q. In that type. Okay, so that's what we're going to do. So how do we do it? Well, the way I did it anyway is I said, well, we do cases on x and y. That is an iterated case analysis. You do a case on x, then a case on y. So I'll do one case here. So one case here is you know that x is in left of x prime and y is in left of y prime. Okay, and there are 3 other cases. They're both in rights and they're crossed up. So you'll have to do all those. I'll just mention the one here. So now with this, so what do we know? By the proof we did last week, I guess it was, we now know something about the paths between x and y. What we know is, well, by applying the previous equation, the case that I'm in, I really have a statement about 2 in lefts, which are written like that. And then by what we proved last week, this must mean that we have, it's the same as having a path between x prime and y prime, because they're both in left. If they're crossed up, it's 0, and then you do a different argument. But this is the main argument. So what we can say is there are P prime and Q prime such that what? Well, now the pattern should be clear. This is the app of in left. There I had to use app2 as a technical convenience. Okay, so but it's the same gist. So this is that. this is app in right of q prime. No, in left also of q prime, of course. They're both q prime, okay? And we know because things are sets, because the types have gone down, we know that p prime is equal to q prime by the assumptions, okay? And so p is equal to q, which is what I needed. Well, I write that, but really there are 3 other cases, okay? But they're all going to exploit the exact same, the lemma that we proved before, the lemma we proved before saying that those 2 things are equivalent. Similarly for in rights, and then the crossed up ones we proved were equal to 0. So you remember we went through the trouble with the cancellation method and all that business, and I wrote that down. Okay, so that's that. So how are we doing on time? Okay, yes?
For the 0 case, like, is there exactly one thing of type, like, 0, 0, arrow, identity between those 2 things? Like, because you just have to abort on either one, right?
Yeah, you just have to abort. I mean, you get this equivalence by an
that type is
abort.
inhabited, right?
Yeah.
The type where you take in the zeros as arguments.
Yeah, I mean, you can go from here to here by having an abort. And if you go from here to here, you have x and y and 0, so you can abort also to get to 0. Is that what you're asking? Because x and y are assumed to be in 0.
Right. I guess it depends on like how x and y are quantified on the left, whether I think that type is inhabited or not.
So what I'm saying is the quantification is, I hope that I didn't do anything wrong. The quantification is at the outside, right? And what I'm saying is for every x and y, so pick your x and y, if these are equal, then, and you have two proofs that they're equal, then those proofs are equal. What's the matter?
It's inhomogeneous.
Is that what?
You're skating very close to a homework problem.
Oh, I see. Oh, all right. I'm sorry. I was stepping on Favonius' homework problem. All right, I won't step on Favonius' homework problem any further. So, all right. So, okay, I didn't realize that. Yeah, I forgot about that. Okay, sorry. Okay, yes, yes, you're right. Okay, good. Okay, so now some other things. So now the others I'm gonna just like assert rather than do them all for you. So it's essentially in the book that NAT is a set. Okay, so you can do that, and you can prove that if A is a set and B is a set, you can prove that A arrow B is a set. This is all based on argumentation we gave before. I'm just repackaging the little lemmas that I proved to you before, and similarly for pi. Now, and now the more tricky one. There are two tricky ones that we have to worry about. And it's actually, I find it kind of interesting to point them out. So you're tempted to say, okay, so ITT is a set theory. Well, wait a minute, not so fast. Not so fast. There are 2 other things to worry about, okay, for ITT, at least as I defined ITT. So the 2 other things to worry about is, if A is a set, Y is id A, and X and Y, let's call it M and N, are in A. Why is it that id AMN is a set? So we have to think about that. I'm going to do an argument so it would be easy to overlook. Okay. And then why is the universe a set? Okay, those are the 2 things that would be questionable. Okay? Then if let's say I resolve these positively, then I will have said ITT is a set theory. Okay, which is interesting just as an observation, but it also accounts for something that was a thorny, contentious issue for decades, which is that, what happens is ITT as conceived as a set theory. In fact, CIC, up until recently, a mild extension of ITT with inductive types, is also a set theory. And so this resolves an interesting contention. So the point is, you'll also be able to show, because ETT is an extension with UIP and equality reflection, ETT is also a set theory. Okay, before I discuss the technicalities here, I just want to say something about why I'm even doing this. And then for decades, there was this kind of thing, like, which is the better set theory? I'm saying it in a retrospective sort of way. Okay? And so the big struggle for a long time was this is a pain in the ass, okay? And this is not, okay? Because if you're doing set theory, right, that is, remember what set theory means. It says being a set means that there's only one way in which two things can be equal. And if they're equal, then essentially you're saying I have uniqueness of identity proofs, and you're essentially saying that all the loops, for example, are reflexivities. So what's happening is then, what's been happening historically was that in ITT, you were paying all the price of higher dimensionality without having any of the benefits because it wasn't exploited. Whereas ETT has a more direct, okay, it's really a strict set theory, meaning that it's not even up to higher homotopy, it's sort of defined strictly that all the types are sets. And this is like vastly easier to use, provided that the math you're doing is concerned only with sets. So in retrospect, now that we have this sort of setup, we can kind of see that what's going on has been going on for a long time, is a strange kind of bureaucracy that forces you to push around all these proofs of identities, which in the end can only ever be reflexivities. And so there's all this business of schlepping things around and having a coercion between x plus y and y plus x and da-da-da-da-da, and carrying out this, like filing things in pentuplicate to do obvious things. And now we can see why that was the case. For a long time it was like, well, philosophical kind of, thing, but now we can kind of see. So the reason is that this has a dimensionality to it that we're going to exploit very shortly, and is related to this. So now I want to explain, let me skip 7 because I don't have time in the time remaining to do the proof that I'm going to do. So I'm going to do a proof next time. I'll show you what this is, and that will set me up for some other things. So let me say something about the universe being a set or not. And this is another mystery of type theory that is now, in my mind, is now finally resolved. Okay, so the mystery for many years was the elements are codes, or the elements are types. So like in New Perl, the elements were types. And in like the MPS account of ITT, they're codes. So this would be like MPS, for example. The elements were codes. What do I mean by that? What it means is that the universe U could be thought of as inductively defined by some notations. You would have, I don't know what to use, honestly. Sometimes people write overbar. So you'd say nat overbar is a token, which is in U. And then you would say, by one means or another, that the meaning of nat overbar is nat. And then you would say a arrow overbar. I know it's a little ugly, but what can I do? Okay, I have a code for the function space, and I would say, if you give me a code for a function space, then that is the function space between the codes, etc. There are different technical setups for this, but that's like the gist of it. Sometimes this was called the elements of nat, okay, L of nat bar. There were different terminology that people use. But the gist of it is, you defined inductively a set of codes. It was extremely important that it be a set of codes, meaning that, for example, just to give you an example, that the code 1 arrow 1 1 has nothing whatever to do with the code for 1. I just picked that out of the hat, but I mean I could pick other ones, okay? Or the code, 1 arrow 0 has nothing to do with the code for 0. And so on, because they're codes. They're notations, okay? So it's an inductively defined set, and it's not materially different from any other bunch of trees. It's just abstract syntax. That forms a set. You have an eliminator that lets me decode the codes, and everything's fine, except that, there's no equations like this, okay? Whereas in like the New Perl type theory, we decided that types were PERs, and one interpretation of the universe is to say that equality there means they have the same PER, partial equivalence relation over untyped terms. Oh, but in that case, you would say, in something like New Pearl, 1 arrow 0 actually is equal, in some sense, to 0 as sets, meaning that every element of here is an element of here and vice versa, or that 1 arrow 1 could be construed as equal to 1. Well, maybe. It depends on the actual details of the encodings of PERS and so on. So the idea is that in homotopy type theory, and this is what we're doing here, the big thing that is covered by univalence is that, well, these at any rate are equivalences. And therefore, by univalence, are considered to be equal as elements of the universe. And so, as I'll mention next time, it's a very easy exercise to show. This implies that the universe under that interpretation is not a set. So we'll get to that next time, because there's a non-trivial path structure. Why? Because these equivalences have content, and if you're injecting those equivalences in and regarding them as equality proofs, you can kind of feel there are many ways things can be equivalent, and so probably, and I'll be able to prove this, probably the universe is not going to turn out to be a set, okay, which is true. But in ITT, it turned out to be a set because it was arranged to turn out to be a set, okay? In a way that at the time was just like philosophical. Bengt Nordstrom would say to me, well, I'm sorry, but I'm unable to understand any other interpretation of the universe. And so, end of discussion, we could never, that was the end of the discussion, there's nothing else to say. Okay, and so it was a philosophical thing, and it was a very unsatisfying. But now we know, right? If from the point of view of where we stand now, you can say, since we wish this to be a set theory, then we're going to have to do some rigging to arrange that the universe be a set. Because if I take equivalences of types, remember we talked about the origin of higher dimensional structure. If we take equivalences between types to be equations, proofs of equations between them as elements of the universe, as paths, then we're out of the business. Then ITT, so to speak, is not a set. ITT is not a set theory because the universe pushes you out. So now we can kind of say, oh, they kind of, they did that right, actually, insofar as they were trying hard to be a set theory. Although none of this terminology was available, but you could say history validates that there was a good reason to do that. Okay, that's the way it's a retrospective analysis, right? So I'm just saying, from where we stand now, you can see that it was a good move, insofar as you want to axiomatize a set theory. Okay, so what I'll talk about next time is a very quick argument that says, otherwise, if you treat them as types and if you treat them up to equivalence, which is what univalence does, then the universe is not a set, and I will be able to show that this is a set, and that will get me rolling to discussing a lot of other homotopy types, and then we'll continue from there. Okay, so that's the plan. Thanks.